By Tesla, for commercial electric vehicles like the Model Y, the 4680 battery cell boasts a potential energy capacity 5 times that of other electric vehicle batteries at 26,000 milliampere hours. With the 4680 battery cells utilizing fewer raw materials in production, the Texas factory has achieved a significant milestone by making 886,000 cells in just a week, enough for 1,000 Model Y vehicles, each equipped with a 75 kilowatt hour battery pack. Approximately 6 months later, Tesla surpassed 10 million 4680 cells produced and has now hit the milestone of 50 million. What strategic objectives does Tesla aim to achieve by ramping up production of the 4680 battery cells on such a monumental level? How is Tesla advancing the efficiency of their 4680 battery cell production? Tesla now says it hopes 4680 battery cells will be cheaper than those from suppliers by the end of the year. The 4680 is a new cell format supported by new technologies, such as the tabless design developed by Tesla. This is a significant gamble for Tesla, a company that has never produced batteries before. The automaker is competing against giants like LG, Panasonic, and Catl, who are also Tesla's current suppliers. 4680 productions have increased by about 18 to 20% compared to fourth quarter, reaching levels necessary for the Cybertruck, approximately 7 gigawatt hours a year. Expectations are to lead in the Cybertruck development phase with battery production through second quarter by expanding the third and fourth lines in phase 1 while maintaining several weeks' worth of cell inventory to ensure we are ahead of the ramp. As we accelerate, the cost of goods sold continues to drop rapidly week by week due to productivity improvements across the line and increased production volume. This is what Tesla CEO Lars Moravi said. However, he added an interesting remark about Tesla's belief that their batteries will outperform nickel-based batteries from suppliers in terms of cost by the end of the year, as highlighted in the first quarter earnings call.
Our goal, and we expect to do this, is to beat supplier costs of nickel-based cells by the end of the year.
Tesla is currently running one production line and one battery assembly line very efficiently. According to Sawyer Merritt, Tesla will add 4 more lines by third quarter of this year. Tesla also intends to increase its orders for 4680 cells from its suppliers. However, the automaker is known for keeping secrets, as it has not provided specific numbers. Many projects are being developed and promoted to encourage the transition to cleaner transportation, such as the first quarter-mile road in Indiana that can charge electric vehicles and heavy-duty trucks. For Tesla, the company has launched products that make it easier for consumers to afford living costs, such as the Powerwall 3 home energy storage system. The company is currently using 4680 batteries in its Cybertrucks. Tesla states that they have completed 4680 cells in inventory for several weeks, as mentioned in a call following the annual report release. To date, 4680 production is ahead of the ramp, with weeks of finished cells in inventory, and the goal is to keep it that way, ex-Twitter user Sawyer Merritt quoted from the call. Tesla astonishes us with a production of 50 million 4680 battery cells at Giga Texas in Austin. It is known that Tesla's 4680 production has increased significantly as the company is manufacturing batteries for electric vehicles produced at Giga Texas along with other factories. In 1 year, Tesla has produced 40 million batteries, just under 1 million batteries per week over the past year. Tesla's battery production is set to develop further through the production of vehicles equipped with the next-generation platform, starting with the robotaxi. CEO Elon Musk announced that the vehicle will be launched on August 8th. Remarkably, Musk has achieved an impressive figure, taking less than 8 months to make 30 million batteries. The last time Tesla announced a significant milestone in 4680 battery production at Giga Texas was a year ago, in June of last year, when the company reported producing 10 million batteries. Looking at the start of the battery production journey at Giga Texas with a production of 4680 cells for the Model Y. As predicted, the acceleration process gradually took place, but by the end of 2022, the factory had reached a significant milestone by producing 886,000 cells in a single week, enough for 1,000 Model Y vehicles, each equipped with a 75 kilowatt-hour battery pack. By June 2023, about 6 months later, Tesla had surpassed 10 million 4680 cells produced, indicating that the company was producing around 351,000 battery cells every week. Over time, Tesla's battery team at Gigatex has shifted their focus to the Cybertruck, introducing a completely new 4680 cell version with higher energy density for the electric pickup truck. Despite this shift, Tesla was still able to continue enhancing 4680 production at a steady pace, reaching 20 million cells produced. The latest update was provided in March when Tesla revealed they had produced 1.4 million cells in 7 days. Now, the company has announced another significant milestone. Based on the timing of the announcement of the production of the 20 millionth and 50 millionth cells, this indicates that Gigatex is producing an average of about 126,000 cells per day, equivalent to roughly 3,780,000 cells a month. Since Tesla currently only uses the 4680 cells in the Cybertruck, which requires 1,360 cells for the 123 kilowatt-hour battery pack, this means the company is producing enough cells to manufacture nearly 2,800 Cybertrucks per month, more than the number the factory is currently producing. This production rate supports the company's claims in the first quarter 2024 earnings report that 4680 cell production is not a bottleneck for the Cybertruck and means that Tesla is gradually building up a reserve that can be used not only for the Cybertruck but also for other vehicles and programs that will utilize the 4680 cells. From now till October, Tesla may have produced 4680 cells for over 22,000 Cybertrucks. The company previously stated that supplying the 4680 cells would not be a hindrance to acceleration. We do not know the official production rate of the Tesla Cybertruck. However, according to analyst Troy Teslike, who focuses on the Tesla, the production rate remained steady during the period from March to June. Exact numbers based on available VIN registrations are behind a paywall. Reports indicate that Tesla is still only producing Tesla Cybertruck skateboard batches, indicating the steady production rate is roughly unrelated to demand. Not only in Texas, but the expansion in Nevada has also begun bustling. Tesla also confirmed that the expansion of the Nevada plant has commenced. As reported, 2 new production facilities will be built as part of the expansion. A 4680 format battery production facility with a capacity of 100 gigawatt hours per year, and another facility for mass production of Tesla semi-electric trucks. The Semi also uses the cylindrical 4680 cells. Initially, Tesla only produced this type of cell on a pilot line in Fremont before starting the second-generation 4680 production in Texas, helping to significantly increase capacity. The long lead time for 4680 cells has been one of the reasons for the delay of the Semi. According to Tesla, if there were enough cells in stock now, it could be good news for the electric trucks. What makes the 4680 battery the ideal choice for affordable Tesla cars? Let's start with the fact that while the 4680 cells produced by Texas have an energy density of 244 watt-hours a kilogram, note that it's not even the target energy density of greater than 300 watt-hours a kilogram compared to the BYD Blade battery, priced at $61 per kilowatt-hour, achieving only 168 watt-hours a kg. Although cost is certainly a factor to consider, energy density is also a key factor, and with other factors that we'll discuss below. The 4680 is evaluated to be superior rather than inferior. Secondly, the 4680 can be used as part of the structural pack, further reducing overall weight, whereas the BYD Blade battery cannot. Thirdly, Tesla is moving towards a 100% dry electrode process. Currently, they have the positive electrode operating with a dry process, but the negative electrode is still a wet process. By bringing that negative electrode into the dry process, they will significantly reduce energy consumption and have a much lower cost cell. But more importantly, not rely on third parties for production, and even if it only costs the same to manufacture under the BYD name, do you think BYD will sell their cells to others without marking up the price? Additionally, many people wonder why Tesla is producing the new 4680 cells instead of larger ones. Is there something optimal about that size, and does it give an advantage to their vehicles? The choice of the smaller size 4680 cells is not certain, but it may be related to heat dissipation capability. Correspondingly, there's less weight and less space occupied by the outer casing of a large pack, meaning you can pack slightly more energy. And when you use larger cells, the surface area to volume ratio decreases, which is great if you want to retain heat inside. However, this is only useful in cold outdoor temperatures when not driving or charging. But if you are trying to keep something cool when it's actually needed, both while driving and during fast charging, then that's a disadvantage. Tesla uses a glycol liquid mixture circulated around the cells to keep them cool when you're charging or using a lot of energy. So, using larger cells would provide more energy but poses challenges for individual cooling. However, in large quantities, the cost-to-energy ratio may be cheaper by a bit. On the other hand, the secondary benefit of smaller cells is that you need more of them than larger cells, and manufacturing them in larger quantities than larger cells would help reduce cost per cell. Another related cost is that improper heat management and charging habits can affect the lifespan of the battery, at least for commonly used lithium-ion types. Proper management can extend the lifespan to 300,000, even 500,000 miles or more. But improper management, and you might need to replace them at around 30,000 miles, $4,000 to $7,000. So, the current 4680 cells strike a technical balance between keeping the battery cool during usage and the cost of the battery. There are also other criteria such as weight, battery capacity, battery life, how to repair damaged cells within the battery pack, etc. These additional criteria may relate to keeping the battery cool and cost, but perhaps less importantly. The key point is that any technical solution, such as the size of the cells as initially required, is a compromise of multiple criteria, and it aims at minimizing costs to bring affordable vehicles to the market that Elon is targeting. Furthermore, the purpose of the 4680 cell becoming the ideal choice for affordable Tesla vehicles is straightforward due to its larger size compared to previous cell types and its efficient energy integration. The 4680 cell is larger than previous cell types, especially the 2170 and 18650 cells. This larger size allows it to store more energy while maintaining high power and efficiency. The integrated design helps reduce energy loss during energy conversion and transmission, thereby increasing the overall efficiency of the cell. Reducing manufacturing costs is also a priority. The 4680 cell requires fewer components and connections compared to previous cell types such as the 2170. This reduces manufacturing costs by optimizing the assembly process and material usage. Using fewer cells to achieve the same driving range and performance also helps reduce the overall cost of electric vehicles. In terms of fast charging efficiency, the cell is capable of faster charging due to its improved electrical and chemical design. This reduces charging time, improving convenience and user experience. Faster charging times also benefit customers and enhance Tesla's competitiveness out there in the market. Lastly, the ability to supply affordable vehicle models is facilitated by the reduced manufacturing costs and enhanced performance of the 4680 cell. With reduced production costs and improved performance, the 4680 cells make it more feasible for Tesla to integrate them into its affordable vehicle lineup. This helps Tesla expand its market and compete with other low-cost electric vehicles, which also helps them achieve mass production goals and up their sales. The 4680 cell not only improves the performance and features of Tesla vehicles, but they also help reduce manufacturing costs and charging time, making the production of affordable electric vehicle models more feasible and ultimately more appealing to consumers. What types of batteries can be used in the Tesla Model 2? The new Model 2 Redwood 2025 battery has some unique features that are attracting attention. Previously, the most common type of EV battery was lithium-ion. However, a significant challenge with this type of battery is the scarcity of lithium supply chains. Chile, holding the world's largest lithium reserves, estimated at about 9.3 million tons in 2023, and while the United States only owns about 1.1 million tons. China leads with 3 million tons, accounting for 62.9% of the global lithium production, far surpassing the United States. This poses headaches for electric vehicle manufacturers as they face lithium scarcity in the market. The current market explains why many car manufacturers have to import batteries, especially from China, because the Chinese government announced in December last year that they would revoke tax credits for models containing Chinese battery components starting in 2024. So, how can Tesla's new battery be developed with Catl and still qualify for tax credits? According to the South China Morning Post, Tesla plans to expand battery production in Nevada by opening a small facility using unused equipment from Catl. This facility will be fully controlled by Tesla, with the company covering 100% of the costs, and Catl personnel will not be involved unless they help install this equipment. This arrangement ensures that Model 2 still qualifies for tax credits because the battery will still be considered. Tesla's domestic competitors, such as Ford, are also taking similar action, with Ford CEO Jim Farley announcing at a press conference that Ford Motor Company will be collaborating with Catl and invest $3.5 billion to produce electric vehicles. The battery plant in Marshall, Michigan is the epicenter of Tesla's battery development conducted by Catl. The overarching initial plan of Tesla Part 3 indicates that Model 2 will use LFP, that's lithium iron phosphate cells, along with a 53 kilowatt-hour capacity battery. The advantages of LFP cells in the chemical field include significantly lower costs for the battery pack, combined with enhanced safety. Additionally, LFP cells provide high working voltage, extended design life, and make charging and discharging the battery compact and fast. However, LFP cells also face challenges regarding low energy density. To address this issue, Catl's introduced an advanced solution with the M3P battery, which is expected to be integrated into Tesla's products in the future. Tesla's models from China using the M3P battery are attracting attention with an impressive energy density of 210 watt-hours a kilogram, representing a 15% growth compared to traditional lithium-ion batteries. This Catl product has been intriguing due to the incorporation of new LFP cells designed for fast charging and superior performance in cold weather. This advanced battery technology, called pin shaking, is generating significant interest with its remarkable fast charging capability. Reports indicate that pin shaking can extend the range by up to 400 kilometers in just 10 minutes of charging, even in very cold weather conditions. Furthermore, at temperatures as low as -10 degrees Celsius, this battery can achieve a charge level from 0 to 80% in only 30 minutes, matching the charging speed of electric vehicles in normal temperatures. The impressive debut of pin shaking foreshadows that Tesla's Model 2 could inherit similar or even surpassing advancements in the future. How fast can Model 2 charge? What might charging a Model 2 look like? Motor Trend tested the Tesla Model S and found that it took 51 minutes to charge from 5% to 95% using the V3 supercharger and Tesla's latest LFP battery. Previously, charging a Tesla took about an hour, but now it's becoming a thing of the past with advancements in battery chemistry. In Model 2, Catl's batteries are capable of fast charging even at low temperatures. For example, the XED vehicle equipped with the new Xantic battery can charge to 80% in 24 minutes under cold conditions at -20 degrees Celsius, and it can add an additional 400 kilometers of range in just 10 minutes. If Catl uses this battery technology in Tesla's Model 2, then full charging might only take 13 minutes, providing a range of 350 kilometers. This charging time sets a new standard that few competitors can match, as most cars today require at least 40 minutes or more to charge. For example, the second generation of Hyundai's Kona can charge to 80% capacity in 47 minutes via DC charging. This also surpasses Chinese competitors like the BYD Dolphin, priced under $14,000 and taking about 41 minutes to achieve similar results. Considering that Model 2 is expected to debut no later than sometime in the middle of next year, Catl and Tesla still have plenty of time to introduce even higher quality batteries for Model 2, enhancing its charging capabilities and overall performance. Well, that'll do it for today's video. We hope you experienced the utmost relaxation after watching our product. If you did, we humbly ask that you please press the like button and join the Tesla Car World community by subscribing to our channel. Just hit that notification bell icon and you can stay tuned for any fantastic videos coming your way. Also, your feedback and time are very much appreciated. If you look up Tesla batteries, they typically have a capacity of 250 to 260 watt-hours a kilogram, allowing for a range of around 320 miles. So if a battery achieves a density of 500 watt-hours a kg, as Elon Musk plans to put in his EVs, what would happen? It's easy to think of numbers like 600 or even the 700-mile range. What seemed impossible and only appeared in this dream is now very close to reality, as Catl has developed a type of battery called a condensed battery, the highest energy density battery currently out there, and it's been confirmed to be manufactured by the end of the year. With this type of battery, the race among automakers will become more explosive than ever. Whoever gets it first will win. So why would Elon Musk be hard-pressed to overlook this battery? In the face of the rapid development of electric vehicles and the expensive, mundane nature of conventional lithium-ion batteries, it's clear that numerous new types of batteries are being researched to elevate electric vehicles to a new level. However, the challenges are numerous because not every type of battery succeeds and becomes an ideal replacement for lithium. As you know, lithium batteries have become the gold standard for automakers worldwide, but finally, something truly promising has emerged. At the Auto Shanghai exhibition, China's contemporary AmpereX technology, Catl, drew significant attention by announcing their breakthrough development of a new condensed battery. With an energy density of up to 500 watt-hours per kilogram, it far surpasses the 200 to 300 watt-hour kilogram range of conventional lithium-ion batteries. Catl also stated that this represents a 70 to 80% increase over current NCM batteries, which is astounding. Catl is confident that if these condensed batteries are used in a standard electric vehicle today, they will improve the driving range by more than 80% without increasing the weight of the battery pack. The company asserts that the superior energy density of the new battery will usher in a new era for high-performance electric vehicles and even electrified passenger aircraft. This time, Catl truly aims to use this battery to mark a significant advancement in battery technology in the transportation industry. If this battery truly achieves such remarkable energy density, we believe it is leading the world, considering that solid-state batteries only reach up to 400 watt-hours a kg. What does this mean for electric vehicles? Well, it means they can travel much longer distances on a single charge using smaller and lighter battery packs. It also means that Catl's condensed batteries have the potential to become the preferred choice. So what is a condensed battery, and how did Catl achieve such greatness? The knowledge about condensed battery may still be new to most of us because, after all, it is a new type of battery. Its structure may also seem confusing, but we will summarize it for you. You need to know that any type of battery has four main components: anode, cathode, separator, and electrolyte. Catl's condensed battery uses a gel polymer electrolyte, a semi-solid product with condensed electrolytes, and new anode and separator materials. Catl uses a semi-solid electrolyte to adjust its mesh structure and regulate the interaction forces between its polymer chains. The company claims that this improves electrical conductivity and lithium-ion transport within the electrolyte while enhancing the stability of the microstructure, thereby improving the safety of the battery. The new type of battery utilizes condensed electrolytes resembling biometric materials with high electrical conductivity to enhance the electrical conduction efficiency of the cells. This, in turn, improves the transport efficiency of lithium ions while enhancing the stability of the microstructure. If you don't understand, here's the simplest example. Okay, imagine you have a toy car that needs batteries to run. Catl is a company that manufactures a special type of battery that helps toy cars run faster and last longer. These batteries use a special material, like a kind of magical clay, to mimic how things work in nature. This magical clay-like substance has tiny grids inside, like spider webs. These grids can change how they stick together, making it easier for electricity to flow through them. This helps the battery provide extra energy in the toy car, making it run faster and last longer before you need to recharge. Catl stated that the condensed batteries integrate a range of advanced technologies, including high-density cathode materials, improved anode materials, separator, and manufacturing processes, delivering excellent charging and discharging performance as well as a good safety performance. During the presentation, it was evident that Catl manufactured these batteries in pouch form and prismatic cell configurations that were showcased. So why is this condensed battery important to Tesla? What advantages does it have? Of course, currently Tesla, as well as Elon Musk, have not made any moves related to this type of battery because we all know that using any type of battery requires a long period of monitoring for suitability and performance that the battery provides for electric vehicles. However, the potential for Elon Musk to bring it to Tesla is not non-existent, considering only the relationship between Catl and Tesla, as well as the immense energy density of condensed batteries. Negotiations could still take place at any time. So, why do we think these condensed batteries are suitable for Tesla's electric vehicles? Here's why. Around 2030, the United Kingdom will ban internal combustion engine cars, and many European countries as well as U.S. states are also following this trend. It's no coincidence that the U.S. government has created a federal tax credit of $7,500 to encourage people to buy electric. In the next decade, buying a gas-powered car is going to be difficult. But when it comes to electric cars, including Tesla, even though their performance has improved significantly in recent years, many still have concerns about their relatively limited range. It's clear that Tesla's unable to reach a 500-mile range over the years, with a Model S currently leading at 402 miles. The first and most obvious benefit of such high energy density batteries is to increase the range of Tesla's electric vehicles. A cell with 500 watt-hours a kg replacing a cell with 250 watt-hours in a pack would double the range of an electric vehicle that can travel with a battery of the same weight or have the weight of the pack to achieve the same range. In other words, a luxury car that could go 300 miles on a single charge can now hit up to 700 miles in a day's drive without needing to recharge. With an energy density of 500 watts per kilogram, if installed in a Tesla Model 3 long range, which typically travels around 341 miles, it'd get a range of nearly 700, even 800 miles, because the weight of the car is significantly reduced with this condensed battery pack. The Model 3 long range currently uses 2170 cells, with a specific energy of 0.269 kilowatt-hours a kilogram. If they were replaced with Catl condensed batteries with half a kilowatt-hour per kg, the operating range would increase by 86%, which is truly astounding. These breakthroughs in battery technology will open up new business models, facilitating the transition to sustainable electric vehicles with various applications. With these condensed batteries, Catl currently emphasizes its tremendous energy density without disclosing other technical specifications such as charging efficiency, charge-discharge rates, safety range, and lifespan. But according to our recent observations, the new battery technologies of manufacturers will almost all adopt 4C charging technology to allow the battery to have an extremely crazy charging speed. The two new batteries, Shenzhen and Shenzhen Plus, both charge to 80% in just 10 to 15 minutes without any problems with life degradation. Even with the sodium-ion battery that Catl's developing, the full charge time is only 10 minutes. So condensed batteries are definitely going to inherit this technology or even do better, because we cannot know what Catl is going to achieve in the future. The world's leading battery manufacturers always got the craziest inventions and achievements, you know? It'd be fantastic to know more about the cost and materials used in manufacturing these types of batteries. If they aren't too expensive when produced on a large scale, then the issue of electric vehicle range will be completely eliminated, ultimately leading to the eradication of internal combustion engines. However, it's disheartening that alongside operational metrics, Catl hasn't disclosed any information about the cost of the new cells or the materials required to produce them at the product launch event in Shanghai. Catl's decision not to disclose the cost of condensed batteries could indeed imply that they haven't achieved a reasonable price point yet. This is understandable because everything is still in the early stages, and they may not have even entered production lines to estimate costs accurately. However, considering the average price of Catl's existing battery types, they still remain relatively affordable compared to the general market prices. The price of Catl's batteries are indeed experiencing a significant decline. By 2024, the cost of Catl's lithium iron phosphate up to around $56 a kilowatt hour, with expectations to further go down to $36 by the end of the year. While cost time, we suspect that customers will have to wait a while before these 500 watt-hour a kilogram cells become affordable enough to be used in competitively priced cars on the market, including what Tesla has to offer. How long until the condensed battery can be mass-produced at scale? Catl is indeed massive, truly massive. If you think companies like Samsung produce a lot of batteries, that's just a drop in the bucket compared to Catl. Last year, they accounted for about 34% of the total new lithium battery capacity. This makes them the world's largest battery manufacturer with absurd profit margins because their output is twice as high as LG Energy, who holds second spot. Therefore, manufacturing a new battery technology is never a big challenge for them. As for condensed batteries, Catl has stated that the new manufacturing process could enable mass production of these batteries to begin by the end of the year. Wu Kai, Catl's chief scientist, stated the company is collaborating with undisclosed partners to ensure that condensed batteries meet safety and quality standards for use. Not only for electric vehicles, Catl also announced that due to the small size and high safety of condensed batteries, they will be first used in the aviation sector, especially for manned electric aircraft, as an experiment to assess their application for electric vehicles simultaneously. Catl's collaborating with several companies to utilize these batteries, and the manufacturers will be announced soon. The reason why these condensed batteries become necessary is because until now, commercial lithium-ion batteries haven't provided enough energy to fully electrify aviation. By nearly doubling the energy density, Catl opens up the possibility for short and medium-range aircraft to run entirely on batteries. Manufacturing batteries that meet aviation-grade quality and safety requirements poses its own challenges, and the battery giant sees its new condensed battery as a final breakthrough that'll propel electrified aviation forward. The only reason there's any skepticism about putting batteries on planes is because batteries are usually heavy and the last thing a plane needs is any more weight. But Catl's condensed batteries solve all that through materials, and now we can fly like birds without running out of power or exploding in midair. We vaguely recall a year or two, perhaps Elon Musk or Sandy Munro, saying that the high-energy density batteries needed for flight were technically possible but prohibitively expensive for most other uses like cars. If this condensed battery is successful for electric aviation, it's likely that Elon Musk will soon have a successor company, which isn't entirely out of the question given his desire to electrify every vehicle in the world and his ambitions for aviation. Why condensed batteries will soon be in electric vehicles? If you carefully observe Catl's new battery technologies, you'll clearly see that Catl's not just a dreamer, but also a doer. Catl not only talks the talk, but walks the walk when it comes to all new battery technology soon to be featured in electric vehicles. And surely condensed batteries are no exception. Now, let's see how Catl has managed to create seemingly impossible battery technologies. In 2021, Catl introduced the first-generation sodium-ion battery with an energy density of 160 watt-hours a kilogram, promising to increase it to 200 watt-hours a kg for the next generation. In early April of this year, the manufacturer also confirmed that Chery in China would become the first automaker to utilize sodium-ion battery technology. Unlike lithium-ion batteries, sodium-ion batteries use sodium instead of lithium as the primary element. Sodium-ion batteries have several advantages such as low raw material cost, high safety, temperature independence, and suitability for fast charging. They're like the salt of the earth, both literally and figuratively. However, they also have some drawbacks such as lower energy density and shorter lifespan, making them less appealing as an energy storage option. As a result, sodium-ion batteries have been largely overlooked by most automotive manufacturers. But Catl persists with it because the manufacturer believes that sodium is much more accessible than lithium and can be found in many places such as seawater, soil, even within our bodies, potentially making sodium-ion batteries a viable alternative to lithium down the road. Catl seized this opportunity and developed its own sodium-ion batteries, improving energy density and lifespan, potentially making them compatible with existing lithium-ion battery systems. According to Wu Kai, their sodium-ion battery exhibits excellent low-temperature performance and fast charging capabilities. It can withstand temperatures as low as -20 degrees Celsius and charge up to 80% in just 15 minutes. This means that people in cold regions can finally benefit from electric vehicles without worrying about freezing or waiting for hours to recharge. Barring any unexpected issues, this will be one of the world's first mass-produced sodium-ion batteries. In over a decade since its establishment, Catl has consistently focused on developing and delivering practical products. In 2022, Catl introduced the Quillen battery, applying CTP, that's cell-to-pack technology, and ternary lithium materials. CTP stands for cell-to-pack, meaning that battery cells are directly integrated into the battery pack without the need for separate modules or intermediate components. This reduces the weight and volume of the battery pack while enhancing energy efficiency and safety. Achieving an impressive system energy density of 250 watt-hours per kilogram, it has become one of the highest energy density ternary lithium batteries out there today. This advanced technology has quickly been put to use. The smart electric SUV XPeng 001, equipped with Quillen batteries, can easily surpass 1,000 kilometers on a single charge and will be delivered to customers this year. Catl not only manufactures batteries, but also works wonders in technology. Ideal, a recent partner of Catl, has announced that they'll use the Quillen batteries to support 4C charging, enabling a 400-kilometer range to be fully charged in just 10 minutes, faster than drinking a cup of coffee. This charging speed is nearly equivalent to refueling with gas, but without the smell and pollution. It's no surprise Time magazine honored the Quillen battery as one of the best inventions of 2022. Truly a marvel of engineering. It's worth noting that lithium batteries have been reaching saturation for decades, and according to some experts, so-called solid-state batteries are just inflated flames with promises. They've been touted as the next big thing, but have never been able to deliver on their promises. However, Catl's condensed batteries, with their remarkable data, have the potential to become a significant milestone in the history of energy storage. We've achieved what others could only dream of. There's a sense that while others are still talking, Catl has been doing. In fact, Catl has always been a doer, not just a talker. In over a decade since its establishment, they have consistently focused on developing and delivering practical and innovative products like condensed batteries. Catl was established in 2011 and is considered the world's largest manufacturer of lithium-ion batteries. By 2022, the company held a 37% global market share in electric vehicles and a 43.4% market share in large-scale energy worldwide. Catl supplies Tesla with lithium iron phosphate batteries for its Shanghai factory in China, and Ford Motor Company has announced plans to build a factory in Michigan to manufacture LFP batteries using technology that's licensed from Catl. We hope Catl will begin mass production of condensed batteries this year. Then we'll be able to see how much they cost and how long they'll last, as Catl has indicated plans to use them in various applications, including cars. We hope they'll be reliable or even better than the conventional cells used today. While initially condensed batteries with high energy efficiency may come at a higher price, competition will drive the prices down, and over time, they may become cheaper than current types of batteries. This is because condensed batteries have higher energy density, requiring less material per kilowatt hour of stored energy, and thus have the potential for cheaper production. Price reductions could happen quite rapidly, and we predict that battery prices will significantly decrease in the coming years. So, what do you think about the potential of the condensed battery for electric vehicles over the next few years? Will Elon be bringing it to Tesla? We hope you'll have the most relaxing feelings after watching this video. If you did, please hit the like button and join the Tesla Car World family by subscribing to our channel. And don't miss out on any of our awesome videos by hitting the bell icon. We value your feedback and your time. People are slowly but surely embracing electric vehicles, EVs, yet the transition still needs to accelerate to achieve the goal of net zero emissions by 2050. Despite numerous advancements in EVs, many drivers are still reluctant to depart from the convenience of gasoline-powered cars. However, the emergence of two new types of batteries, sodium-ion batteries and solid-state batteries, brings hope for a cost-effective and efficient solution. With projected manufacturing costs dropping to around $40 per kilowatt hours by the end of this decade. Solid-state batteries with energy densities ranging from 400 to 500 watt-hours a kg and the ability to charge up to 80% capacity in just 10 to 15 minutes not only extend the driving range but also minimize charging time. With these advancements, the question arises, solid-state batteries or sodium-ion batteries, which will be the superior choice for a greener future? What battery technology is establishing a new benchmark for electric vehicles, solid-state batteries or sodium-ion batteries? The development of next-generation batteries is gaining momentum as it is a crucial factor in the future of energy storage, and it holds the key to carbon reduction and energy transition amidst the challenges of climate change. Energy storage for renewables not only makes energy production more flexible, but also ensures the integration of renewable energy into the grid. Now, let's explore the 5 differences between these two types of batteries, considering the future of the electric vehicle industry. First, let's consider energy density. Solid-state batteries are considered the next generation of battery technology, particularly in the electric vehicle EV industry. They utilize solid electrolytes instead of liquid electrolytes in conventional lithium-ion batteries, offering several key benefits, including higher energy density, improved safety, and longer lifespan. These batteries can achieve energy densities ranging from 300 to 500 watt-hours a kilogram, compared to the current 250 to 300 watt-hours a kg of lithium-ion batteries. Research by BMW has shown that solid-state batteries can provide double the energy density of standard lithium-ion batteries, making them an attractive choice for EV manufacturers looking to optimize vehicle performance and range. Meanwhile, sodium-ion batteries are also seen as another potential option for electric vehicles, using sodium instead of lithium. Sodium is a more abundant and cheaper element compared to lithium, making sodium-ion batteries a cost-effective solution. However, the energy density of sodium-ion batteries is currently lower, ranging from 130 watt-hours a kg to 160 watt-hours a kg, but is expected to increase to around 200 watt-hours a kg in the future. Although not as high as solid-state batteries, this still surpasses the theoretical limits of LFP devices. Moreover, in terms of power density, sodium-ion batteries can achieve 1 kilowatt a kg, higher than the 340 to 420 watt per kg of nickel manganese cobalt NMC batteries and 175 to 425 watts a kg of other battery types. This indicates that despite having a lower energy density than solid-state batteries, sodium-ion batteries still have significant potential due to their stability and lower cost. When comparing the two advanced battery technologies, cost is a key factor to consider. In the realm of lithium metal solid-state batteries, the U.S. Department of Energy, DOE, has been leveraging this technology to drive robust growth in the EV market, albeit still facing cost challenges. In the context of solid-state metal lithium batteries, the DOE considered figures in 2023 and projected a cost of around $320 a kilowatt hour. However, they anticipate this cost to decrease to a more competitive range from $70 to $120 per kilowatt hour. Estimated production costs for solid-state batteries this year are $153 a kilowatt hour, significantly reduced from the $1,355 a kilowatt hour back in 2008. These cost reductions are attributed to advancements in battery technology and chemistry, along with increased manufacturing scale. By 2025, predicts that production costs for solid-state batteries and other advanced types could decrease to $60 a kilowatt hour. As for the cost of sodium-ion batteries, market research company IDTechX, based in the UK, states that sodium-ion batteries with multi-layer metal oxide cathodes and hard carbon anodes will have material costs about 25 to 30% lower than lithium iron phosphate LFP batteries. However, significant initial savings may be challenging to achieve as this technology requires time to scale up. IDTechX calculates the average cell cost for sodium-ion batteries to be $87 a kilowatt hour. By the end of this decade, the production costs of sodium-ion batteries, primarily using iron and manganese, may bottom out at around $40 a kilowatt hour, equivalent to $50 a kilowatt hour at the pack level. In the latest report on sodium-ion technology, experts predict that battery production capacity will exceed 100 gigawatt hours by 2030. By 2025, capacity could significantly increase, with investments expected in 2024. Through this analysis, it is evident that while current solid-state batteries may have higher costs, with positive cost reduction forecasts, they could become a viable option in the near future. Meanwhile, sodium-ion batteries with lower costs and significant scalability potential may prove to be an attractive solution for large-scale energy storage applications and transportation. When it comes to safety, both types of advanced batteries have their own characteristics. Solid-state batteries are often hailed as the holy grail due to perceived advantages such as improved safety, higher energy density, longer lifespan, greater durability, wider operating temperature range, tighter stacking, simpler battery design, and potential for mechanical flexibility. By replacing organic liquid electrolytes with solid electrolytes, these batteries get more resilient and safer. Moreover, solid electrolytes may be compatible with high-voltage cathode materials and high-capacity lithium metal anodes, pushing energy density beyond 1,000 watt-hours an L. However, most solid-state electrolytes tend to have higher densities than liquid electrolytes, especially inorganic solid electrolytes, often thicker than separators used in conventional lithium-ion batteries. If the electrode composition remains unchanged, still using graphite anodes and multi-layer metal oxide cathodes, most solid-state batteries will have a lower energy density per weight compared to lithium-ion batteries. Additionally, some argue that thermal management systems may be eliminated for solid-state batteries due to their safety. However, this is not entirely accurate. Solid-state batteries may have different safe operating zones compared to lithium-ion batteries. Thermal management systems and other protective measures are still necessary. Solid-state batteries are highly regarded for safety due to their use of solid electrolytes instead of flammable liquid electrolytes found in conventional lithium-ion batteries. Solid electrolytes not only reduce the risk of leakage, but also eliminate the risk of explosion due to internal short circuits. Solid electrolytes have higher thermal tolerance and are less prone to decomposition at high temperatures, enabling solid-state batteries to operate safely in more challenging conditions. Additionally, because solid-state batteries can maintain a more stable structure during charging and discharging, the formation of dendritic crystals, a common cause of short circuits, is significantly reduced. As for sodium-ion batteries, despite their lower energy density compared to solid-state batteries, they still offer considerable safety. A notable aspect of sodium-ion batteries stems from the use of sodium, a more abundant element with fewer reactive properties than lithium. This reduces the risk of explosion and enhances chemical stability. Materials used in sodium-ion batteries, such as multi-layered metal oxide cathodes and hard carbon anodes, tend to be stable and durable under thermal and mechanical stress. An IDTechX report indicates that sodium-ion batteries can operate safely at temperatures up to 100 degrees Celsius compared to around 60 degrees Celsius for conventional lithium-ion batteries. Furthermore, because sodium reacts less with water and air than lithium, handling and transporting sodium-ion batteries are safer, reducing the risk of accidents during production and use. The performance of these two types of batteries in different conditions will be as follows. Solid-state batteries excel in operating at low temperatures. Solid electrolytes do not freeze like liquid electrolytes in traditional lithium-ion batteries, ensuring good performance even at temperatures below 0 degrees. Specifically, research has shown that solid-state batteries can operate reliably at minus 20 degrees Celsius. On the other hand, sodium-ion batteries exhibit relatively good performance at low temperatures, although not as good as solid-state batteries. Due to the chemical properties of sodium, sodium-ion batteries can tolerate temperatures around minus 10 degrees Celsius without significant performance degradation. However, even at lower temperatures, the performance of sodium-ion batteries may decline. Solid-state batteries demonstrate superior heat resistance with solid electrolytes that don't vaporize or decompose at high temperatures, thereby reducing the risk of explosion. This allows solid-state batteries to operate stably at temperatures from 80 to 100 degrees Celsius. In contrast, traditional lithium-ion batteries may encounter issues or reduce performance at temperatures above 60 degrees Celsius. Sodium-ion batteries also exhibit stable performance at similarly high temperatures as solid-state batteries, thanks to the stability of sodium and other materials used. Experiments have shown that sodium-ion batteries can perform well at temperatures up to 60 to 80 degrees Celsius, which is advantageous for applications in high-temperature conditions. Solid-state batteries have superior fast-charging capabilities due to their ability to withstand high currents and forming dendrites, one of the main causes of short circuits and failures. Experiments have demonstrated that solid-state batteries can charge up to 80% of their capacity within 15 to 30 minutes without significantly affecting battery lifespan. While sodium-ion batteries also have fast-charging capabilities, they are not as superior as solid-state batteries. Research has indicated that sodium-ion batteries can charge up to 80% of their capacity within 30 to 45 minutes without causing significant lifespan or safety issues. This makes sodium-ion batteries a feasible choice for applications that need fast charging, albeit at a lower cost. How do these two types of batteries affect the environment? According to a study by Transport and Environment (T&E), solid-state batteries can reduce the carbon emissions of electric vehicles by about 39%, while also indicating that producing solid-state batteries from sustainably sourced raw materials could further mitigate the climate impact of batteries. New mining techniques such as recovering lithium from geothermal wells are considered to have less environmental impact compared to traditional mining methods associated with lithium sourcing from clay deposits and spodumene. Meanwhile, also dubbed as the least harmful type of battery to humans compared to modern types, sodium-ion batteries are primarily attributed to their use of sodium instead of lithium. This minimizes the risk of environmental pollution and health-related issues during the handling and recycling of sodium-ion batteries. They also have the lowest water pollution levels among various battery types, helping to reduce negative impacts on precious water resources and aquatic ecosystems. Although sodium-ion batteries have a moderate impact on resource depletion and soil acidification, they still have a positive impact compared to many other types of batteries because the use of sodium can reduce dependence on rare resources and minimize the extraction and processing of natural resource materials. What challenges need to be addressed for these two types of batteries? Regarding the challenges of solid-state batteries, especially under fast-charging conditions, affects the battery's lifespan. Solid electrolytes do not conduct ions as effectively as liquid counterparts, impacting both the power and energy of the cell. Solid-state cells require high temperature and external pressure to operate efficiently, adding complexity to packaging design. Furthermore, solid-state cells necessitate high manufacturing precision and numerous technical improvements to be mass-produced cost-effectively. While the potential benefits are appealing, it's crucial to acknowledge the challenges hindering widespread solid-state battery production is the most significant hurdle. Technological barriers are undeniable as many companies strive to develop reliable and cost-effective solid electrolytes capable of withstanding harsh automotive conditions. A technical challenge actively being addressed. Generally, solid-state electrolytes are more brittle and temperature-sensitive than liquid counterparts, making safe implementation crucial. Improvements in solid electrolytes may take another 5 to 10 years to achieve the necessary stability. Expanding production scale to meet automotive industry demands is a significant obstacle. Raw material procurement needs careful consideration, and batch production processes require enhancement and optimization to make solid-state batteries economically viable. The global solid-state battery production capacity currently stands at around 2 gigawatt-hours, but to meet market demand, the figure needs to increase to at least 100 gigawatt-hours by 2030, demanding significant investments in technology and infrastructure. Additionally, cost considerations are paramount. Currently, solid-state battery production costs are relatively high compared to traditional lithium-ion batteries. Achieving cost parity or cost-effectiveness is crucial for widespread adoption. The production cost of solid-state batteries currently fluctuates around $400 per kilowatt hour compared to around $150 a kilowatt hour for lithium-ion batteries. However, with advancements in technology and production scale, experts predict this cost could decrease to $80 to $100 a kilowatt hour within the next decade. Although the timeline for widespread adoption of solid-state batteries remains uncertain, there are promising developments. Major automaker and battery manufacturers are heavily investing in research and developments to overcome current challenges. Breakthroughs in solid-state technology are expected to accelerate the pace of bringing products to market. As for challenges of sodium-ion batteries, industry experts predict that solid-state batteries may begin penetrating the automotive market by the mid to late 2020s. However, initial implementation may be limited to high-end electric vehicles before getting widespread. Of course, sodium-ion batteries also face their own challenges, particularly in commercialization and competition with existing battery technologies. One of the main challenges is the lower energy density compared to lithium-ion batteries. Currently, sodium-ion batteries have an energy density of around 130 to 160 watt-hours a kg, while lithium-ion batteries typically achieve between 250 to 300 watt-hours a kg. This means that sodium-ion batteries need to be larger and heavier to provide the same energy level, limiting their use in applications requiring higher energy density, such as electric vehicles. Furthermore, the charging and discharging efficiency of sodium-ion batteries also needs improvement. Although sodium-ion batteries can fast charge up to 80% capacity in about 30 to 45 minutes, they still do not reach the fast charging levels of solid-state batteries, which can achieve the same level of charging in 15 to 30 minutes. The ability to withstand high currents without dendrite formation remains a significant challenge to improve the performance and durability of sodium-ion batteries. Additionally, the lifespan of sodium-ion batteries currently cannot compare to their counterparts. According to some studies, the lifespan of sodium-ion batteries is around 1,000 to 2,000 charge-discharge cycles, while lithium-ion batteries can get up to 3,000 to 5,000 cycles. This means that sodium-ion batteries need to be replaced more frequently, increasing the overall long-term ownership costs. On the other hand, the manufacturing process of sodium-ion batteries, although similar to lithium-ion batteries, still needs to be optimized to ensure economic efficiency. The cost to convert a lithium-ion battery manufacturing plant to produce sodium-ion batteries is estimated to require an additional 10% capital cost. But to achieve large-scale production and reduce production costs to competitive levels, the industry still needs significant investment in research and development. Lastly, another challenge is the development and standardization of raw material and supply chains for sodium-ion batteries. Although sodium is more abundant and cheaper than lithium, establishing a stable and sustainable supply chain to meet the growing market demand remains an issue to be addressed. While sodium-ion batteries have great potential, overcoming challenges related to energy density, charging, discharging efficiency, lifespan, manufacturing processes, and supply chains is necessary for them to effectively compete with current battery technologies and contribute to the future of renewable energy storage. The future prospects of these two types of batteries for the automotive industry are very promising. Improvements in solid-state batteries are opening up exciting prospects for the automotive industry. Like any new policy and product, the development of electric vehicles has faced many challenges, but the benefits of solid-state batteries are causing great excitement in the automotive industry. Vehicles equipped with solid-state batteries will have a strong competitive advantage, helping dealerships stand out with advanced technology, attracting forward-thinking consumers, and differentiating themselves from competitors. These improvements are also enhancing customer satisfaction with longer driving ranges, faster charging times, and increased safety, contributing to a better electric vehicle ownership experience. Satisfied customers are more likely to become repeat buyers and support dealerships. Moreover, with longer lifespans and lower maintenance requirements, solid-state batteries can significantly reduce total ownership costs, an attractive selling point for cost-conscious consumers. Many automakers have announced that electric vehicles using solid-state batteries will appear around 2025 and will see significant growth by 2030. Some are developing their own solid-state technology, while others are collaborating with partners, including startups and established companies. In fact, some automakers and partners are establishing new joint ventures to bring solid-state batteries into electric vehicle production. Solid-state batteries are not only safer than lithium-ion batteries, but also have higher energy density due to their 3D architecture design with higher theoretical power, providing a wider operating range from batteries of the same size as current lithium-ion packs. Research and development projects are also striving to reduce the cost of solid-state batteries, with some estimates suggesting that the final cost could be more than 30% lower than that of conventional batteries today. Once solid-state technology meets these promises, there will be very few reasons for automakers to continue using traditional lithium-ion batteries in electrical vehicles in the future. Tesla, a pioneer in EVs, is poised to maintain its leadership position by carefully selecting and optimizing the type of battery it uses. With its commitment to innovation, Tesla is likely to embrace solid-state batteries, capitalizing on their higher energy density, faster charging times, and longer lifespan compared to traditional lithium-ion batteries. By investing in research and development, forging strategic partnerships, and leveraging its manufacturing expertise, Tesla can ensure that it remains at the forefront of electric vehicle technology. Choosing the right battery technology will enable Tesla to continue offering cutting-edge vehicles that redefine the automotive industry and drive the transition to sustainable transportation. We hope you'll experience the utmost relaxation after watching this video. If you do, please press the like button and join the Tesla Car World community by subscribing to our channel. Hit the notification bell icon to stay tuned for any fantastic videos coming your way. Your feedback and time are highly appreciated.